All right, we're recording. Good morning, everybody. So welcome to module number 7 for Math 174. We are already in week number 11. Kaunti na lang, ano? Parang may nakita akong student na nag-post kahapon. Medyo nagpanic ako. Hindi, kanina, mga 3 a.m. Nakita ko nag-post siya ng isang memory na 20 days to go na lang daw before the semester ends. So nagpanic ako bigla. Kasi hindi ko nakita na memory pala siya way back from 2020 or 2018. Sabi ko, bakit 20 days na lang? Patapos na ba talaga yung semester? So yeah, as late ko na-realize, ano lang pala, memory lang pala. But the thing is, parang hindi na ron nalalayo kung ilang araw na lang yung meron tayo. No? Because we're already at week 11, the usual semester has 16 weeks. So probably more or less we have 5 more weeks to go. And I guess Math 174 has 12 modules or 11 modules. I forgot exactly the number is, pero siguro saktong-sakto yung mangyayari sa atin, ano. But and then probably I can take off one module off from the shelf. So pwede nating bawasan para meron tayong medyo may breathing space between the last problem set or the second problem set and the final project. Anyway, I guess you deserve it because week in and week out you're doing a lot of things, ano. Pero I saw your comments in the problem set na medyo nag-enjoy naman kayo paggawa ng ng laboratory exercise. You're getting something new in the laboratory exercise, things that I might not had been able to mention in the lectures. But yeah, that's really how I designed the lab exercise, for you to get something new. Hindi lang siya para i-test or ipa-apply sa inyo yung mga methods, pero para makahugot kayo ng insights because sayang yung 3 hours sa lab. So you should get something out of it. Not really just to prove to me that you learned, but also for you to gain some insights as you draw hands-on experience on using these methods. Ano? And medyo related doon, itong module number 7. Module number 7 is all about improving numerical differentiation techniques because I hope this is what you feel about numerical differentiation. Mas madali siya sa interpolation. Kasi parang andaling mag-derive ng differentiation formula. You should decide how many points you will use. Will you go forward, backward, or centered in terms of the data points? And what's the order of the method that you want to use? Ano? Tapos, you'll just rely to Taylor's theorem para kunin yung expansion ng mga non-f of x data points na gagamitin mo dun sa formula. Then you'll solve a system of equations. You might have several degrees of freedom to contend with. Pag may free variables, pwede ka mag-invento or mag-impose ng kung anong gusto mong free variable para makakome up ng sarili mong numerical differentiation formula. And using the formulas that you derive is not a biggie as well because pwede nyo gamitin sa Excel spreadsheet. Hindi nyo kailangan magpaka-high-tech at gumamit ng MATLAB or gumamit ng Python para sa simpleng numerical differentiation, right? Pwede nyo gawin sa Excel yung computations. No one will judge you for that. Kasi mas madali nga siya sa Excel kasi isang drag lang ng formula or isang copy-paste lang ng formula, you can easily get your approximate for the derivatives, ano? So madali siyang gawin. And then yung theoretical foundation niya simple lang din. However, there could be some anomalies in this numerical differentiation formulas, and this is a nice illustration of the interplay between theoretical error and the propagated error. Kasi dito natin makikita na yung formula na derive natin on paper is one thing, implementing it on a computer is another thing. So that's what module number 7 will tell us. How do we take into account the totality of the errors, meaning you have the theoretical error and the propagated error, and how do we optimize our numerical differentiation formulas in terms of the different factors that affect the entire process. So after module 7, you are expected to be able to find the optimal step size for the machine implementation of a numerical differentiation formula, which might sound little absurd because I will show you again later na theoretically, parang ang alam natin, paliitin mo si H. Mas gaganda yung approximation, right? Kaya lang, bakit merong option number 1? Bakit meron daw find the optimal step size? So, ibig sabihin pala, ang implication ng objective number 1, hindi sufficient na paliitin natin yung value ni H dun sa ating differentiation formula, which runs counterintuitive to the notion that we have seen earlier that as the increment approaches 0, the error in the differentiation formula will approach 0. But I hope you have seen this in your laboratory exercise last Monday na, oo nga no, bakit ganoon? Pag maliit masyado si H, pumapangit na yung error. And I think a couple of you asked me that, Sir, tama pa ba yung ginagawa ko? Kasi ang ganda ng approximation ko, 10 to the negative 1 si H, 10 to the negative 2 hanggang 10 to the negative 5th. Pero pag lumampas na ako doon, everything go awry. So hindi natin nakukuha yung expected answers kasi nagzi-zero yung sagot, lumalaki yung error at hindi nyo matanggap. You are probably blaming yourself. Bakit? Ano na naman ang mali dun sa code ko? Ang tagal kong kinode sa MATLAB itong numerical differentiation formula. Saan ako nagkamali? Saan ako nagkulang? I hope you realize it's not you. It's your computer that's failing you. All right? But more on that later. And then the second is we want to devise a way to accelerate the convergence with respect to H of our numerical differentiation formula. We have noted when we derive our formula, yung order, siya yung nagsasabi gaano kabilis nagko-converge sa true derivative yung approximates, right? Pag meron kang formula of order 2, ibig sabihin the error is of order big O of H squared. The error in the approximation theoretically approaches 0 as fast as how H squared approaches 0. Magkasing bilis nagsi-zero si H squared at saka yung error. Kapag ang formula mo ay order 2. Alright? Pero may paraan ba that we can make our approximation faster? I mean, in terms of convergence, meaning, can we make a formula of order big O of H squared into a better formula so that the error will go to 0 faster than how H squared approaches 0. Yun yung titingnan natin on Thursday. And then as usual, you will be tested sa lab expert to use your improved numerical differentiation formulas to solve scientific problems. Okay. Okay. Now, to illustrate the need for the optimal step size, let's look at this. This is a 3-point centered formula of order 2. Okay, for the first derivative. Okay, so I hope you can easily derive this. Ito nga ba yung nasa module number 6 na example? I forgot exactly what that is, but I think nung sinulat ko to medyo interdependent yung mga sections. So I guess this is one of the formulas. Oh yeah, sinabi ko revisit na ginamit natin from the previous module. So this is a classical formula or approximation formula for the first derivative. 3-point centered, okay? Kasi ginamit natin si f of x plus h. Si f of x ay somewhere, pero na-cancel out siya, pero supposedly kasali siya dito. At saka si f of x minus h. Kaya siya centered formula, 3 points yung ginamit. Tapos the error is negative h squared over 6 f triple prime of c. So siya ay order 2. Okay? So what we learned last time, nagsi-zero yung error dito kasing bilis ng pag-zero ni h squared up to a constant scaling factor f triple prime of c all over 6. Okay? And then when you analyze this, okay, tingnan ko yung error term. Tapos yung error term, pag kinuha ko yung limit nito as h approaches 0, magzi-zero. So ang ibig sabihin ng limit statement na to, habang si h ay palapit ng palapit kay 0, dapat talaga magzi-zero yung error. Okay? Oh, by the way, guys, this is what I refer to as the theoretical error. Okay? Because this is the error that is due to the formulation of the method itself, right? Doon dinerive natin, kinuha natin yung Taylor series expansion ng f of x plus h, f of x minus 2h. And then we did our algebra, our cancellation thing to come up with a formula for f prime. Yung truncated term dun sa Taylor series expansion, ito yung natira. Alright? Kaya ito yung theoretical error. Ito yung error na nanggaling dun sa derivation ng method mismo. Alright? And true enough, when we take the limit as h approaches 0 of the theoretical error, we get 0. Ibig sabihin, yung error ay magze-0 kapag ka si h ay nag-approach ng 0, which makes sense, right? So this limiting procedure will tell us, kung gusto mo ng super accurate na approximate, gawin mo lang si h super lapit kay 0. That's what we see on paper. That's what we see in practice. And that might be true if you will be doing everything by hand, carrying out all of the calculations tediously by hand, no truncation, no estimation. You use exact values all of the times. Okay? Yun yung sinasabi nito. Kaya lang syempre, gumagamit tayo ng technological tools. Gumagamit tayo ng computers, calculators, or spreadsheets to give us our estimates. Alright? So tingnan natin, ano yung mangyayari kapag in-approximate ko si f prime of what? F prime of 0 kung si f of x ay equal kay e to the x. Well, sir, bakit kapag nag-numerical differentiation formula, usual to, bina-validate natin yung method, and see if we get the expected behavior. So the derivative of e to the x is e to the x, evaluate it at x equals 0. So we are trying to approximate 1. Tapos ang gagawin ko, gagamitin ko tong formula na to with f of x equals e to the x para i-approximate si 1 or f prime of 0. Okay? And then I will use this using varying step sizes like what you did in the laboratory exercise last Monday. So ayan, gumawa ko ng table dito. So kapag ang step size ay 10 to the negative 1, ang error ay order 10 to the minus 3, which is somewhat good, right? Pag ang step size ay 10 to the minus 2, 1.67 times 10 to the negative 5 yung error, yung absolute or relative error. In this case, equal lang yung absolute saka yung relative error. And which is as expected, right? Lumiit yung step size. So lumiit din yung absolute error. So intuitively, our data makes sense. And then moreover, remember that our theoretical error is big O of h squared. Magsing bilis si h squared at saka yung error pupunta ng 0. All right? And do we get the expected performance of our method with respect to convergence with respect to h? Well, yes, at least for the first step. Because here, nabawasan ng one order. Nabawasan ng isang order yung step size. From 10 to the minus 2, it went down to 10 to the negative 1. From 10 to the negative 1, bumaba siya sa 10 to the negative 2. So meaning the step size decreased by 10 times. So nag-decrease ng 10 times yung ating step size. Ito ay formula of order big O of h squared. So ibig sabihin, dapat ang epekto ng division by 10 dun sa step size, dapat madi-divide ng around 10 squared yung error. Kasi degree 2 yung ating formula. So whatever happens dun sa step size, all right, by what factor you decrease it, madi-decrease by that factor squared yung ating error. Kasi nga order big O of h squared ito. So pag dinivide mo by 10 yung step size, yung error dapat madi-divide ng something around 100, which is 10 squared. And that happened, right? Because here, you look at the orders. From 10 to the minus 3, it went down to 10 to the negative 5. So at least for the first step, it's true. Nag-work as expected yung method. Bumaba yung error, and not just that, bumaba ito by following the trend h squared. Right? Then let's go one step further. Babaan ko pa, i-divide ko ba by 10 yung step size. So now I'm at 10 to the minus 3. So again, I incurred a 10 times of scaling down of the step size. All right. So meron akong 10 to the -1 na introduced factor dun sa step size, all right? Now, look at the error. The error is, yeah, 2 orders down, which is expected kasi 10 to the -1, quantity squared, 10 to the -2. So 10 to the -2 yung bagong factor dun sa relative error. And the trend will follow. The trend in the step size lang naman, nagdi-divide ako ng 10, so nababawasan by 1 order yung step size. Being a formula of order big of h squared, dapat yung error nababawasan ng 10 to the -2. Nababawasan ng 10 to the second power every step of the way. True enough, we have 10 to the -5, 10 to the -7, 10 to the -9, 10 to the -11. Everything worked as expected hanggang 10 to the -5. But after 10 to the -5, the process starts to break down. Because, okay, 10 to the -6 yung h, hindi nabawasan by 2 orders yung error. Because if I have done everything purely in paper, I expect this guy to be something times 10 to the -13. Following it will be something 10 to the -15, and so on. Dapat nababawasan ng dalawa yung exponent habang binabawasan ko ng isa yung exponent sa step size. But everything fails because nag-underperform na yung ating method. Actually, hindi nga lang siya nag-underperform nag-worsen yung approximation na nakuha natin, because if you look at this, sa 10 to the -8 na h, we expect to get better approximate than what we have gotten from, say, 10 to the -5. Because the principle, as h goes to 0, the error will go to 0, but that's not the case. Sa 10 to the -8, ang error natin ay 10 to the -9. Pero sa 10 to the -5, ang error natin ay 10 to the -11. And the worst case, kapag 10 to the -16 na yung step size, tataas ng 44.5% yung error. Okay? Which again, should ring some bells to you. If you are a novice numerical analyst, and if you just perform this from the first time, you might be baffled. And this is the experience of some of you when doing the laboratory exercise. Saan kayo nagkamali? Well, the blame is not on you, but on your machines. The problem is machine precision. Okay? Because remember, when you have a very small value of h, that means x and x plus h, as well as x minus h, will be very, very close to each other. Right? Kasi ang liit na ng increment. Kapag masyado nang maliit yung increment, those numbers become indistinguishable from each other. Tapos ang gagawin ni computer kasi nagtatruncate siya to some decimal digits. So ibig sabihin, kung super magkakalapit si x plus h, at saka si x minus h, at saka si x, which happens when h is very, very small, then those data points that you used may be treated by the computers to be the one and the same, thing, right? Tapos magkakaroon ka na ng cancellation error. Okay? Just to go back to this formula, halimbawa si h ay super small. Kung napakaliit na ni h, si x plus h at saka si x minus h will be very, very close to each other. And if they are close to each other, okay, or they are close to each other, na along the or within the machine precision, baka tingnan ni computer si x plus h at saka si x minus h to be exactly the same thing. Right? Kasi di ba ang ginagawa ni computer, pag meron akong mahabang decimal or meron akong non-repeating, non-terminating na number na in-input sa computer, ang gagawin ni computer, hindi niya ini-store lahat ng decimal digits. Finite yung mga computing machines natin. So ang gagawin niya, kukunin niya lang halimbawa yung first 16 decimal digits. Alright? And that's doing a lot. So if it saves the first 16 decimal digits nung iyong number, kapag yung step size mo ay mas maliit na sa 10 to the -16, ibig sabihin, pag nag-truncate ako sa pang-16 na decimal digit, yung dalawa kong number ay magkamukha na. Posibleng yung f of x plus h at saka si f of x ay magkamukha na. Kasi nga, first 16 digits lang yung aking kino-cover. Kapag yung step size ko ay 10 to the negative 17 or 10 to the negative 18, so virtually h is 0. Nag-add ako ng 0 kay x para makuha si x plus h at saka si x minus h from the computer's point of view. So kung halos equal na, or technically virtually equal na sa computers, si x plus h at saka si x minus h, so yung f of x plus h at saka si f of x minus h will be virtually the same thing. Again, from the lens of the computers. All right? So ito ay equal dito. So magkakaroon ako ng difference ng two numbers. Then ito ay magzi-zero. Yun yung tinatawag natin na cancellation error. Because we are subtracting two numbers that are very close to each other, or two numbers that have come from computations involving two numbers that are very close to each other, and when we are subtracting them, nakakakuha tayo ng 0 even if we should get a number greater than 0. So yun yung tinatawag natin na cancellation error. So when h is very, very small and it is smaller than the machine precision, then this will always bring back a value of 0. Kaya dun sa lab exer nyo, posibleng nakakuha kayo ng mga zeros doon sa approximate nyo para sa derivative, which rightfully rang some bells for you, na may red flag dito, teka lang. Wala dapat zero dito kasi ang in-approximate nyo ay e, right? So that happened due to cancellation error. Or if you're lucky enough that your h is not very close to the machine precision, pero nag-evaluate ka pa rito ng function value, ano? So, posible na, okay, si x plus h at saka si x minus h, magkaiba pa rin from the point of view of the computer. But when you plug them into your function f, baka naman yung f of x plus h at saka f of x minus h, ang difference nila ay less than 10 to the minus 16 or less than the machine precision. Halimbawa, ito ang difference nila ay 10 to the minus 18. Pero yung machine precision mo ay 10 to the minus 16. So ang gagawin ni computer mo, kukunin niya lang yung first 16 decimal digits. Yung first non-zero decimal digit mo pa mangyayari sa 18th decimal place. So ibig sabihin, magzi-zero pa rin or i-consider pa rin ni machine na 0 si f prime. So magkakaroon ka pa rin ng cancellation error. And that caused the underperformance of the method. So the theoretical error tells us that as you decrease h, your error will decrease by h squared. Kasi nga formula of order 2, itong nasa table number 1 na in-implement natin. Pero that will not happen when we implement the method in a computer, because we need to take care of the truncation error. The truncation error is the error from the conversion of a floating point number to machine readable number or machine manipulable number. Kaya marami nagtatanong, na-experience ko na to, siguro mga 10 beses ko na itong sinagot sa email. Sir, bakit po magkaiba yung nakuha natin sa splines? Tama po yung 5 pero yung 2 C's ay magkaiba po tayo. Alright? Now, nung chinek ko, magkaiba nga tayo ng value nung 2 parameters o nung 2 constants, pero sila ay mga order lampas na ng 10 to the minus 16. Kapag nakita kayo sa modern computers, sa usual computers, ng 2 numbers na order 10 to the negative 16 or less, they are virtually considered to be 0. Kasi I think the IEEE standard ay ang machine precision ay a constant times 10 to the negative 16. So virtually, when you are doing computations, double precision, which is the default for most computers, ay 10 to the minus 16 yung kanyang machine precision o yung machine epsilon na tinatawag. So when you get a number that is smaller than 10 to the negative 16, that is virtually considered to be 0 from the machine's point of view. Although our computers can store numbers with far more accuracy than 10 to the negative 16, but when calculations are carried out, parang 10 to the negative 16 yung default na accuracy. So every after operation, kino-convert niya sa machine precision, which is around 10 to the negative 16, yung mga numbers. Okay? So kaya yeah, sa Excel chineck ko uli yung chineck ko yung webpage ni Microsoft Excel. I think the machine precision in Excel is is 2 to the negative 52, which is something around it's an order big of h to the negative 16. All right. So ganun talaga. Ito yung default. Ito yung industry standard. Unless you will tinker around the default kay MATLAB nyo o sa computer nyo, ang default ay 10 to the negative 16. Kaya you don't want, when you're doing a machine calculation, you don't want to make your h smaller than 10 to the negative 16. Tapos ang dami ko namang sinasabi, dapat nakita niyo na 'to sa math, sa AMAT 152 Dapat tingin ako sa oras 9:10 na, so I just have 10 minutes. So let's move on. Now, how do we combat this phenomenon na hindi pala natutupad yung theoretical error? Kasi aside from the theoretical error, dapat nating i-consider yung error due to machine truncation o yung tinatawag na truncation error. So when we do an error analysis, we just don't stop when we get the theoretical error, especially if you're anticipating that you will be using a computer in order to do the computations for you. So laging merong at least dalawang source ng error, theoretical and the truncation error. Yung truncation error, ito yung dahil yung computers natin ay finite machines, hindi nila kayang i-store lahat ng significant digits ng ating number, lagi yan magta-truncate at some point. And we need to also factor that truncation in. Okay? To do so, let's do a quick analysis para dito sa formula na to and find what's the best step size. A step size that is small enough so that it will make our theoretical error small, but not large enough to give us a blowing up truncation error. Right? So ang gagawin ko ngayon, i-quantify ko ito. For instance, in our formula above, kailangan natin yung f of x plus h, right? So to have better notations for everything, kapag kailangan natin yung f of x plus kh, where k is an integer, all right? So pag kailangan mo si f of x plus h, f of x plus 2h, f of x minus 2h, so pwede natin tingnan siya as f of x plus kh, where k here is 1, k here is 2, k here is negative 2. Okay? Yung f of kh na kailangan mo dun sa formula mo ng differentiation ay hindi talaga sinisave ni computer as f of x plus kh. Yung value na to, kukompute ni computer, pero when the double precision kicks in, gagawin niya, i-round off niya to with respect to dun sa machine precision. So instead of f of x plus kh, ang ginagamit sa computations ng computer natin ay yung truncated version niya na y sub k. Alright? So halimbawa, ang nasa formula mo ay f of x plus 2h. So here k equals 2. So ang nire-read ni computer ay hindi yung eksaktong f of x plus 2h. Ang nire-read niya at ini-store niya sa memory for use in the computations later ay si y sub 2 o yung y sub k natin. Right? Pinuputol niya si f of x plus 2h to the number of significant digits allowed. So ibig sabihin doon, meron kang truncation error. Sabihin natin yung truncation error ay si e sub k. Ito yung truncation error. Tapos ito yung machine readable number. Machine readable number. Okay? So ang eksaktong value ni f of x plus kh ay y sub k plus e sub k. Pero ang gagamitin ni computer sa kanyang computations ay y sub k lamang. Kasi si e sub k, ito yung mga na-etchapwerang decimal digits dahil finite yung ating computing device. Okay? So essentially, pagka in-apply mo yung 3-point centered formula of order 2 na ginamit natin para magawa yung table, hindi ito yung kinocompute ni computer. Hindi ito eksakto yung kanyang kinocompute. But instead, ang kinocompute niya, ito napapalitan ng y sub 1. Okay? Kasi ang k dito ay 1. Tapos ito napapalitan ng y sub negative 1. Alright? Divided by 2 times h. ito yung kinocompute ni computer, hindi ito. Kasi nga, finite lamang. Nag-round off siya sa bawat number. Pag may nakita siyang isang number, i-round off niya yon bago niya i-save sa kanyang memory. Tapos, yung computations, i-call niya yung number na nasa memory niya, hindi yung eksaktong sagot ng previous computations, i-call niya yung nakasave sa memory niya, which has the most number of decimal digits allowed. Okay? So kaya sa pangarap lamang natutupad or nai-implement perfectly yung formula. Kasi once gumamit ka na ng computer, ito yung nakukuha mo. Right? So, pero in practice, dapat ito yung kinocompute ng computer. Hindi lang si y sub 1. Dapat ang kinocompute niya o ang ginagamit niya ay si y sub 1 plus e sub 1. Binalik mo yung na-truncate na term. So this is what the computer does. This is what we expect it to do. So expectation versus reality. All right? So now, instead na ito yung ibigay sa atin, ito exactly yung ibigay sa atin ng computer, ito yung binibigay niya. Pero ito yung formula of order big O of h squared. Okay? Ito, meron na tong additional error. Aside from the theoretical error, there is what we call the error due to machine truncation. Alright? So, kailangan nating i-factor in yung error dun sa yung error due to the truncation dun sa ating error analysis. Kasi nga, in-implement natin to using a computer. So, tingnan natin, ano ngayon yung total error? Hindi na lamang yung theoretical error or yung error due to the derivation of the formula. Titingnan na, isasama natin sa analysis yung error due to the machine implementation. So, now the error will be quantified by the exact f prime of x minus what the computers will give us. Ang binibigay niya ay hindi yung approximate natin para kay f prime, hindi ito. Ang binibigay sa atin ng computer ay si f prime tilde. Yung number na nakuha niya by implementing the formula that we derive pero dun sa truncated function values. Okay? Kaya yun yung nilagay ko rito. Okay? So, ito, f prime tilde. Nakita natin, ito yan. Alright? Kasi ma-minus ko siya dun sa exactong derivative. Tapos, i-expand ko itong y1 minus y sub negative 1 all over 2h. So, you just play with this expression. Then, combine some terms. Paano ko ba ito kinombine? Hold on. Yeah. Nexpand ko lang siya. Yung y1, sinulat ko siya na y1 plus, pinalitan ko siya ng y1 plus e1. Pero to maintain this to be equal to this guy, kailangan bawiin ko yung minus e1 na dinagdag ko. Alright? So, ito, yung y1, pinalitan ko ng y1 plus e1. So, mababago yung quantity. To retain this equality, ima-minus ko yung e1 dun sa dulo. Ganun din yung e sub negative 1. Instead na y sub negative 1, pinalitan ko to ng y sub negative 1 plus e sub negative 1. Pero obviously, ito ay hindi na equal dito. To maintain the equality between the two terms, mag-subtract ako ng e sub negative 1 over 2h dito. So basically, I added and subtracted e sub 1 minus e sub negative 1 all over 2h. Gusto ko yon para i-group ko naman ito at saka ito. Tapos ito, alam ko na, ito yung truncation error. Yung total truncation error. Okay? Bakit ko gustong i-group itong dalawang yellow? Gusto ko silang i-group para ito ay f prime minus this guy. But do you recognize this guy? This is the exact, or this should have been the theoretical implementation of the formula. Kasama yung tinuncate na decimal digits. So basically, this term is just our theoretical error. Ito yung error na na-derive natin dun sa formula. Kasi nga, ito ay yung eksaktong f of x plus 2h, f of x plus h minus f of x minus h all over 2h. Ima-minus ko siya sa f prime. Alam na natin, yun yung theoretical error. Yung theoretical error ay ito. tas kinopy over ko lang yung itong truncation error. So essentially, the total error in this routine is this guy. Hindi lang yung theoretical error. Ito alam na natin. Na-factor in natin to dun sa analysis natin when we derive the formula. Ito yung error dahil dun sa theoretical derivation ng method. Pero meron pa siyang kaakibat na isa pang number, which is the error due to machine truncation. The error due to the truncation error. Ito yung error. This is the cost of being lazy and asking our computers to do the job for us. Ito yung kailangan nating i-consider once gumamit ka na ng computing device para i-implement yung numerical differentiation formula. So dapat ito yung ina-analyze natin. Ano yung nangyayari kapag ka si H ay nag-approach ng 0? Okay? Kapag ka si H ay nag-approach ng 0, alam natin yung theoretical error mag-approach ng 0. Pero when E sub 1 minus E sub negative 1 is not equal to 0, meaning this numerator is a constant, a non-zero constant, divided by something that approaches 0, ito ay magbe-blow up to positive infinity. Right? Or positive or negative infinity. So, tanggalin ko na lang yung sign para sure. Ano? So, that means the total error will approach infinity when we make H very, very small. Kasi nag-appear si H dito sa denominator dito. So, mag-zero yung theoretical error, pero pag super liit na ni H, lalaki naman yung truncation error. And this is what happened, right? So up to some point, there's a perfect harmony with the theoretical and the truncation error. So kapag ka pinababa natin si H, lumiliit yung ating total error. Ito yung nakita nyo sa exercise mula kay 10 to the negative 1 hanggang kay 10 to the negative 5. Kasi dun may perfect harmony. Yung theoretical at saka yung truncation error. Pero once you go beyond that, if your H is small enough so as to make the truncation error more significant than the theoretical error, lalaki na yung error mo. Kasi kung makikita mo, habang si H ay lumiliit, palaki ng palaki yung truncation error, which is as expected. Right? Kasi mas papalapit na ng papalapit yung mga X values na kinoconsider mo dun sa formula, mas nagiging prone ka na sa cancellation error. So the question is, what should be our H? Gusto natin si H ay hindi kalakihan at hindi rin kaliitan. Kasi kung masyado siyang maliit yung ating theoretical error, pero lalaki yung truncation error. Pag masyado siyang malaki yung theoretical error, maliit yung truncation error. So we need to strike the perfect balance. Kailan natin makukuha yung best approximation by minimizing the error. So ang gagawin nyo, i-derive nyo yung total error. Katulad ng ginawa natin dito. Kung may formula kayong consider dati, kunin nyo yung theoretical error, i-consider nyo yung truncation error. Okay? May shortcut dun sa pagkuha ng truncation error. Si Y1, so meron siyang truncation error na E1. Tapos copy, and then si Y sub negative 1, meron siyang truncation error na E to the negative 1. So lahat dito ng Y sub K, papalitan mo lang ng E sub K. The reason why you can do that, pwede nyo i-pattern dito. Pero essentially, yung total error or yung truncation error dito sa formula na to ay nakuha ko by replacing the letter Y's by the letter E dito sa differentiation formula na to. Okay? So, but you can see na ito yung dahilan kung bakit nangyayari yun. So in general, this is your total error. So ang gagawin natin, i-minimize natin itong theoretical error o yung absolute value niya. So kunin yung absolute value ng theoretical error, ng total error, tapos i-optimize nyo with respect to H. Hanapin nyo yung best H that will minimize the absolute value of the error. And in this case, madali lang siya. Okay. Ito si E of H. Ito yung total error. And this will be different from formula to formula. So try to compute the total error dun sa formula na nakuha nyo sa laboratory exercise last Monday. Kasi probably, yun din yung ipapagamit ko sa inyo sa susunod na lab excerpt. Right? Tapos kunin nyo yung absolute value niyan. So absolute value niyan ay, hold on. h squared over 6, absolute value ng f triple prime of c. And this guy is a constant with respect to h. Constant yan, di yan nagbabago. Hindi nga lang natin alam yung number niya, pero alam ko constant yan. Plus, absolute value, actually less than or equal na pala to, no? Kasi magta-triangle inequality na ako. E1 plus E sub negative 1 all over 2h. So gumamit ako ng ng triangle inequality rito. Nagkaroon to ng absolute value, naging plus to, nagkaroon ng absolute value, you get this. You get the larger number. And then so this is a constant. This is something that depends on the machine precision. Okay. So this guy now is less than or equal to h squared over 6. Then I'll replace this by the upper bound for f triple prime of c. Papalitan ko siya ng m, where capital M is an upper bound. Sinulat ko ba rito? Yeah. M is the maximum value of f triple prime. So, laging pessimistic tayo. Ano yung pinakamalaking posibleng value ng absolute value ni f triple prime? Sabihin ko siya si M, kunwari. So, paltang ko to by a positive number M, which is the largest possible value of the third derivative of f at the interval x minus h hanggang x plus h. So, typo lang yan. Okay? So, papalitan ko lang siya ng m. Tapos, etong E1 and E2. Remember, ito yung truncation error dahil sa nag-round off ka. Okay? And this is constant from in a machine. So, tawagin natin epsilon, yung upper bound sa E sub k. So, we will assume that the absolute value of E sub k is bounded by a machine epsilon. Usually, machine epsilon ay 10 to the minus 16. But let's keep epsilon for now. So, magkakaroon dito tayo ng plus 2 epsilon all over 2h. And then, pwede kong i-cancel yung 2. Ito yung matitira. So, essentially, yung total error ay bounded by h squared over 6 times m, which is the largest possible value of the absolute value of the third derivative, plus epsilon over h. Ito yung estimate natin, upper bound estimate natin para dun sa error. Then we want to find h such that this is minimized. So gusto kong i-minimize itong quantity na to by picking h. So pwede ko itong tawagin, ito yung function, tawagin natin itong function, anong letter? Nagamit ko na si E. So tawagin natin ito yung what? Nawalan ako ng tawag sa error function. Sige, tawagin natin itong alpha of h. Yan yung error function alpha of h ko. Remember paano tayo nagbe-minimize ng isang function? Kunin mo yung derivative na gusto mong i-minimize. So, to ay h over 3 times m minus epsilon over h squared, yung derivative niya. Equate mo yan sa 0 para makuha yung critical numbers. May isa ka lang critical number dito. Ang critical number mo rito for h ay, so you solve for h, I guess what you get is the cube root of 3 epsilon all over m. Okay, just do the math kasi overtime na ako. So, kunin mo yung derivative. So, simplify mo yung total error, right? Kunan mo siya ng upper bound, palitan mo yung f triple prime of c by a constant m, which you know is the upper bound. Tapos, yung epsilon over h, yung epsilon, ito at saka ito, palitan mo lang parehas ng epsilon. So, you'll have 2 epsilon all over 2h. So, essentially, you will get epsilon over h. So the total error is bounded above by h squared over 6 times m plus epsilon over h. Ito yung worst case scenario para dun sa total error. So gusto nating hanapin si h that will drive this value down. Gusto ko siyang palitin. So paano ka nagbe-minimize? Balik ka sa Math 36. Oy, may silbi naman pala yung ginawa natin ng Math 36. So you solve for the critical number first by taking the derivative, equating it to 0. Then the solution to that equation will be your critical number. Tapos magsa-second derivative test ka. I-plug in mo yung critical number mo doon sa second derivative ng function na minimize mo. Tapos pag ginawa niyo yun, makakakuha kayo ng isang positive number. All right. Since this is a positive number, I am sure that this number is the minimizer. Kasi nga positive yung second derivative. Kung naging negative yung second derivative, sabi ng second derivative test, ito ay maximizer. Pero dahil positive naman, we get the number that we desired. This is the optimal step size for our, or the near optimal step size for our numerical differentiation formula. You get something larger than this, your theoretical error would be larger as optimal. Get an H lower than this, machine precision will kick in, it will alter your solution. Okay, so ito yung piliin mo na step size. All right? Huwag mo masyadong palitin si H. Ito lang yung ito yung pinaka best. Redundant, pinaka best na. Pero ito yung best or ito yung near best step size na kailangan yung gamitin. Now, how do you get the exact value of this? Yung epsilon, usually siya ay 10 to the minus 16 for most machines. Or actually, dito pala sabi ko ay yung Excel kong ginamit, yung spreadsheet kong ginamit ay 10 to the negative 15 yung machine epsilon. So for this particular example, ang optimal H or ang near optimal H ko ay 3 times 10 to the negative 15. Okay? So pinlagin ko lang tong epsilon dito. Tapos ano si M? Si M yung maximum value ng F triple prime of X. F triple prime of C. All right? So ang ating f of x ay e to the x. So ang third derivative niya ay e to the x pa rin. Kukunin ko yung maximum ni e to the x, all right? On the interval 1 minus h hanggang kay 1 plus h. Kasi we are evaluating or we are estimating the derivative when x is equal to 1. So ibig sabihin, ang ginagamit kong data points ay si 1 minus h at saka si 1 plus h. Pero kapag ka si 1 minus h, kapag ka si h ay napakaliit na, si 1 minus h at saka si 1 plus h ay super magkalapit na. To a point na silang dalawa ay malapit na kay 1. So ibig sabihin si m, which is the maximum value of the third derivative, would be approximately equal to the absolute value of f triple prime of 1. Kasi nagma-maximize ako sa 1 minus h hanggang kay 1 plus h. Pero pag si h ay super liit na, napakaliit na nitong interval na to na yung function values nila magkakamukha na. Dahil magkakamukha na yung function values nila, yung m, pwede kong i-approximate by the value of f triple prime at any number within this very tiny interval. And the nice number in this very tiny interval ay si 1. So kaya si m ay pwede kong palitan by the absolute value or approximate by the absolute value of f triple prime of 1. F triple prime of 1 is e to the 1, so ito ay e. Okay? And when you calculate this, you will get this to be your, e to the, mali yung iniisip ko pala. Ang x pala natin dito, ay 0. Ang pinapa-estimate ko nga pala si f prime of 0. So you are maximizing the third derivative from negative h to h. Pero pag maliit na si h, si negative h to h, ay parang napakaliit na interval around 0. So you can estimate m by the value of f triple prime at the number 0. So ito ay e to the 0. So cube root lang siya ng 3 times 10 to the negative 15, which is this guy. Ibig sabihin, ito yung optimal step size. Ano to? 1, 2, 3, 4, 5. 1.44 times 10 to the negative 5 yung optimal step size o yung near optimal step size, which is or which matches our observation kanina. Na the best occurs somewhere when your step size is around 10 to the negative 5. 1.44 times 10 to the negative 5. So that is basically within these two values. All right? And indeed, dito natin nakita yung pinakamagandang approximation. All right? Kasi nga, yung optimal step size daw ay nearly 1.44 times 10 to the negative 5. So, wag ka nang bababa doon sa 10 to the negative 5 kasi magkikick in na yung machine precision. Okay?
So sorry guys, super overtime ako ng 15 minutes. Sorry, medyo na-late kasi ako ng gising. So, at saka ang dami ko pa rin sinabi. Pero I hope you get something new today. And yeah, I hope you digested itong topic na to. If not, kasi medyo mabilis na ako, especially dun sa dulo. At medyo kinulang na ako sa kape. Mali-mali na minsan yung naiisip ko. Iba itong mga numbers na. Napaghalo ko yung lab extra at saka itong example na to. So if there are some questions about this or something is not clear, tell me on Thursday. Or if you want to ask it right away, send an email to me, and then magkaklase lang ako ng 151, then sasagutin ko yung questions nyo, right? But if there are no other concerns, salamat guys for bearing with me. Overtime ako today. But let's see each other again on Thursday para naman tingnan ano pa yung isang paraan aside from finding the optimal step size. How can we improve our numerical differentiation formulas? And that will entail accelerating the convergence of the method using what we call Richardson extrapolation. Okay? So thank you guys and see you on Thursday, on Friday, sorry.
Thank you, sir.
All
Thank you,
right.
sir.